Okay. So, now that we have understood this, let us go through one quick example and find out how do we calculate all these things, right. So, you see here, this is the same standard section that we use in all our calculations. Previously in flexure module also we use the same cross section, and this is the blue color line, this is the profile of the tendon, profile of tendon. In addition to that, I also have some nominal longitudinal bar and flange width dimensions are given to you. And eccentricity of the cable at the midspan is 425, at support it is 0, and we are saying that from analysis your beam is subjected to 75 kilonewton per meter of factored load. Concrete strength is taken as 40 megapascal. Area of pre-stressing steel is taken as, you see here, 1390 mm square, and these are all strength properties. 1860 is the characteristic strength of steel, and effective pre-stress is taken as 1100 megapascal. Effective pre-stressing force is 2000 kilonewton, that is nothing but 1100 multiplied by the area of the pre-stressing steel. So, that works out to be 2000 kilonewton. Concrete area is 290,000 millimeter square, and so on, right. And I am going to assume that I am going to use only 10 mm rebar as a stirrup, right, and longitudinal bar I am taking it to be 12 mm because it is a pre-stress section. Typically you try to keep the non-pre-stress steel low diameter with a very minimum, that too from detailing point of view. Most of the time you may not need any additional longitudinal rebar, but you put some nominal non-pre-stressed longitudinal rebar from minimum reinforcement point of view from code provisions. Now, clear cover to the stirrup, we are taking it as 20 millimeter. Width of the bearing I am taking. What is the width of the bearing? The support width, how the beam is or the girder is supported on a supporting element. So, let us say if this is a bridge girder and if it is sitting on the bridge pier caps, you also put elastomeric bearing. Let us say that width of the bearing is 400 millimeter. Now, let us look at now. First step is to do the structural analysis and draw the shear force and bending moment diagram. And you can see the center line will start from 0.2 meter, half of the bearing width. So, we are taking at the face of the support, so which is x is equal to 0.2 meter, right. So, x is basically going to be 0.4 divided by 2, right. So, that is we take this is at the face of the support, right. Now, the shear demand is it is going to be, because now I am taking the shear force at the face of the support. The face of the support is from the center line, it is at 0.2 meter. So, it is going to be total load multiplied by half of L minus x, which is 0.2. It works out to be 547.5 kilonewton. Now, what is moment? Again 0.5 into Wt into Lx minus x square, that works out to be 111 kilonewton meter. Now, let us check the adequacy of the section. I calculate the nominal shear Vu divided by B into dt, that should be less than 4 megapascal for FCK equal to 40 megapascal, right, from table 9. Now, what is dt? Depth of the, what should be the effective depth that you should consider? This is your overall depth minus clear cover, let us assume 20 mm, and diameter of the stirrup, which is again 10 mm, and diameter of the longitudinal bar, which taken as 12 millimeters. So, it is half with 6, 964 it is coming, right. If you substitute that, it works out to be 3.8 megapascal, which is less than 4 meg. So, whatever the section dimension that we have chosen is adequate and it is not going to fail in principal compression mode. If this value tau v is coming to be greater than tau c max, then what we have to do is we have to revise cross section, right, revise cross section. Okay. Now, we have done that. Now, we are going to plot the decompression moment. Okay. And now, what is the expression for decompression moment? Code asking you to calculate 0.8 into FPT into I by Y. Now, what is FPT? FPT is we are calculating the pre-stress at the level of the tendon. So, PE by AC is your pre-stressing concentric stress component. Then I am going to get PE into E is your nothing but your moment, and I am calculating the stress at a distance y from the CGC. So, if you substitute that, now what should be the the eccentricity at a distance x, this is also you have to make sure. Now, we are doing the calculations at support, okay. All these calculations, we are doing it at support, or in other words, depending upon your cable is having a parabolic cable profile. So, the eccentricity of the cable will keep changing depending upon where you are taking the section and doing the calculation, right. So, that is why we need to do. So, the eccentricity, parabolic cable profile, eccentricity can be written like this, where let us say delta is the eccentricity as a variable, 4 into delta into x by L minus 4 delta into x square by L square. So, this is the profile, right. So, we have seen that this is the cable profile, right. So, if I am taking here, so we know this is your eccentricity, let us say this is delta and this is, let us say this is at x, and let us say this is your L, okay. Oops. Okay. Let us say this is your delta and this is where you are calculating this. So, this is your L, right. Now, I am calculating the eccentricity, let us say at this point E. So, this is how we say as an expression, right. So, at x is equal to 0.2, then we can calculate eccentricity as 4 into delta, which is 425 millimeter is the eccentricity at the mid span, times x is equal to 0.2 and then span is 15. So, if you substitute that, you get eccentricity at x is equal to 0.2 is 0.02236 meters. It is a very small eccentricity because we are now very close to the support. Now, what would be the pre-stress at that location of the tendon is, we are calculating basically this is equal to 22.36 millimeter. So, 2000 is the force, 2000 divided by the cross section area will give me the PE by AC. Now, PE into eccentricity, which is 22.36, right, divided by your section modulus, let us say, which is 70.7 into 10 to the power of 6, right. So, that is what we calculate, and you substitute FPT equal to 7.52 megapascal, and M naught works out to be 0.8 into this value FPT that you get, 7.52 into I by Y, which is nothing but your section modulus, which is 70.7 into 10 to the power of 6. So, if you substitute that, M naught works out to be 425.85 kilonewton meter, right. So, like that you do it at different sections, and if you plot it, this is the M naught calculation, right. So, we got this, and this is your demand, okay, bending moment diagram for a simply supported beam. Now, this is the value that we established, which is equal to 425 or so for the M naught, okay. So, let us say this is at okay, maybe this is okay, this is at x is equal to 1.2. So, we did the calculation for x is equal to 0.2 somewhere here. So, somewhere here, right, x is equal to 0.2. So, this is the value that we got, okay, right. Okay. So, now you calculate VC naught and VCR. Why we are doing this M naught calculation? Because it will go into as an input for the VCR calculation. Now, let us calculate VC naught. VC naught, we have already derived this expression 0.67 BW into dt into this component, and you will have vertical component of the pre-stress also. VPE will be PE into sin theta. Now, again, what is PE into sin theta? Again, from cable profile, y is 4 into delta L square into x into L minus x, parabolic equation. The slope is given by the first derivative of this y, which is 4 delta by L square into L minus 2x. Now, tan theta is nothing but dy by dx. So, you substitute that and you get your slope as 0.1103, because at that particular section at x is equal to 0.2, I want to calculate what is the slope of the cable profile, right. So, now what is VPE at that point? It is 2000 into sine. So, which is not very significant, which is not very small. So, even though that angle is 0.11 in radians, you see that that is almost giving me shear resistance of 220 kilonewton, which is not a small value, okay. So, this is the vertical component. vertical component of pre-stress. That is actually going to reduce the shear demand, right? Either you reduce the demand or add to the capacity. You cannot do both. Okay, that's what I told you. So Ft is 0.24 into square root of Fck. We take 1.1 megapascal. Fcp is this, and then if you substitute into this equation, then you get Vc naught as 537 kilonewton, right? Now what is VCR? Now this is your Vc naught. This is a web shear capacity. Okay. Now we are calculating the flexure shear capacity, which is VCR. And what is the expression? Again we derive this expression, which is m naught into V by m. You see this is the shear at flexural crack, plus this is an additional shear that is required to convert the flexural crack into shear crack, right. So that is why we add this, right. So what is FPE by FP, which is 0.59, and rho T, which is your percentage of your pre-stressing steel, 100 into AP by BW into D, and D you take that as 522 or 964, and if you substitute, you cannot take a smaller value, okay. So always, you know, or you have to DT, either you take this value or minimum of 0.8 H should be taken. So just because your pre-stressing cable is at close to the CG, you should not take this D. You have to take either DT or a minimum of 0.8 H in calculation of your amount of your percentage of your steel. Okay, that is why I end up with 0.96. If you take a small value of D, then it will look like you have a lot of steel, which is not correct, right. So percentage will look like a high number, which is not correct. Then you will be overestimating the tau C, which is not correct. So okay, so now that we have done, so in the equation now I need to calculate beta, and beta is 0.8 into square root of 40 divided by 6.89 into 0.96, and we get a value of 0.76, which is less than 1. So if it is less than 1, you take beta equal to 1. So substitute beta equal to 1 in this equation. This is, then you get your tau C or psi Z, whatever. This is your concrete capacity, right, in shear strength. So psi Z works out to be 1.16 megapascal, and you substitute here, and you get your equation as VCR as 2213 kilonewton. Now you see that this is a very, very high value, very high. Why you are ending up with very high value? Because you are calculating the flexural shear cracking capacity at a location very close to the support, where your flexural demand itself is very low. You remember, you see in this equation, the bending moment itself is going to be very, very low, and because of which the section will not actually crack in flexion. So you need large moment to require crack. So this component will become extremely high. So this additional thing that is going to be, this component is going to be extremely high. So you will get very high. So if you use this, so in other words, for section that is not having a lot of flexural demand, it will not be controlled by VCR, it will always be controlled by web shear capacity. So VC will always be VC naught in the sections close to the support, unless you are looking at a section close to the continuous support where you will also have flexural demand. Then the scenario will be different. For simply supported case, close to the support, it will always be VC naught that will control the concrete capacity, right. Shear resistance now, VC is smaller of VC naught and VCR. So we have to take VC naught as 537 kilonewton, right. And you see here, so when we plot these things and you get, this is your shear demand, okay. So this is your 563, 543, all those things. So what is that we are putting here? Okay. Okay, sorry. You see, now when we plot this, we are plotting multiple things. So this is VC, which is your concrete capacity, concrete shear capacity, and this is 50% of concrete shear capacity. The reason, you see, we have to put when the demand becomes more than 50% of concrete capacity, we need to put at those regions a minimum shear reinforcement. That is the reason we are doing this 50% of the concrete shear capacity, and this is your shear demand. Okay. So, now that we have found this, so this is only, so we have to find out wherever that stirrup reinforcement is required. Let us see. Now, at these locations, when you look at it here, you see here the shear demand is, you see no reinforcement is required. Why there is no reinforcement is required is because the VC is higher than V, and it is also higher than 50% of, you see this is, this black is 50% of VC. So, that means from here to here you find that shear demand is less than 50% of VC. So, you do not need any shear reinforcement. At this location you will find that now the green color line, which is the shear demand, is higher than the black color curve, but it is lesser than the red color curve. So, this is the region that you need to put nominal shear reinforcement, or in other words it is a minimum shear reinforcement, right. Then for the region that is on the left side of this line, right, you need to put, because here you find that shear demand is always greater than the red color curve, which is a 100% concrete shear capacity. So, definitely we need to put stirrups, right. So, you see for example, the maximum that the demand that I need Vs is actually working out to be 75 kilonewton. So, what I will do is I will take that maximum and put everywhere for the same amount. But if you want to be optimize it, then you can divide the beam into a number of regions and then choose that Vs, and then you can put that also, right. But now the demand itself is not very high. So, I am going to take 75 kilonewton and put over the entire region from close to 0 to almost to 6 meter, right. Okay. So, now how do we calculate the shear reinforcement for web? The maximum shear stress needs to be carried by stirrups is 75 kilonewton. Let us assume I am going to put 2 legged 10 mm diameter stirrup and area of each leg, that is why I am multiplying by 2. Now, both the legs will be arresting that crack, right. So, that is why I am taking 2 pi by 4 d square. So, it is area is 157 millimeter square, and we know Vs is 75,000, 75 into 1000, and I am calculating, now that I have assumed the area of stirrups, I am calculating what should be the spacing. The spacing required is working out to be 728 mm. You see that this is quite high. So, now we have to go and check for minimum spacing requirements. First one is 2.175 into Fi into SV by B, that works out to be 915 millimeter, but my SV again cannot be, should be less than 0.75 times dt, which is 579 millimeter, or 4 times the width of the web, which is 600 millimeter. So, what is that we need to choose? We need to choose actually 10 mm diameter stirrup actually at, in fact, I should say this, it should be less than both. So, we can say 550 millimeter center to center, right, because this has to satisfy both conditions. So, if you take, you have to take the minimum, which is 579 it is coming. So, either you can put it at 575 or 550 millimeter, right. Okay. Now, in the shear reinforcement for flange, now how do we do that? This is, we are looking at for horizontal shear VH. VH, when you do the calculation, it is going to be shear stress, or tau H, we say you are going to VQ by I into B. Now, what would be the thickness? The thickness will be basically your, you look at the horizontal flange, right. So, VQ by now IVF. Now, what is the Q? Q you will be calculating about this axis, right. So, you are going to calculate this area and you take your Q. So, the Q that you are calculating will be for this area. So, let us now look at how do we do that. So, if you plot your shear stress variations, you will get this nice shear stress variations, in the flange it is going to be like this, and here it is going to be like this, and this value is VH by B by 4I, and in the web we know that the vertical shear is going to be resisted like this and you get this nice value. So, you know how to calculate these things from your strength of materials, but here we are calculating calculations only for the flange, because flange will have the horizontal shear stress. So, that we need to calculate. Now, in general the tau formula is this, right. So, basically what is that you take tau is VQ by I into B. Now, in this case Q I have to, because I am calculating about this axis, right. So, Q will be for this half of the flange area, which is BF into DF by 2. So, that works out to be your area is this, and then when you take the shear demand is remaining same 547.5 kilonewton, area is this we have already calculated, right, and the distance of the area, the moment of the area basically from here to here, if you look at it, it is going to be A1 into dy, which is basically equal to 500 millimeter, and now I is moment of inertia, which is 3.54 into 10 to the power of 10. Now, thickness of the flange will be basically your thickness. So, that is your thickness, basically that is 200 millimeter. So, your thickness will, instead of breadth here, you will be putting your thickness of your flange, because that is the thickness that you are going to in horizontal thing. So, that is what the width that it is going to be for one flange, which is going to be 200 millimeter. So, you find that it is equal to 1.93 megapascal. Now, what is the shear force in the flange is, you integrate that. So, it is going to be tau F max into BF into DF by 4. So, basically you are integrating all the shear stress over the flange area. So, when you do that, you get your forces 48 kilonewton. For the 48 kilonewton, now I can calculate what should be the area of the flange. See, in the flange, now what kind of reinforcement you will be providing. So, basically stirrups for web we know how to put. For flange, we need to come up with this, this kind of a layout for taking care of the horizontal shear, right. This is what the legs that we are trying to calculate. That is the reason the B becomes your thickness of your flange, okay. So, that is why you have here in this case the depth of the flange. Similarly, the moment of the area is also that you are calculating like this, okay, A1 into Y, okay. So, if you do that, you get your SV as 600 millimeter. So, again we have to provide some nominal stirrups, which is 10 mm stirrups at 375 center to center. So, you put some nominal stirrup, because you cannot have more than, say, 600 mm is too large spacing. So, again for that horizontal stirrup requirement also you have to satisfy the spacing requirement. So, spacing cannot be more than 375 millimeters. So, we can put it at 375. So, the flange you can see 10 mm stirrup at 375 center to center. For web, I am putting 10 mm stirrup at, maybe this should be 500, like 550 we said, 550 you can put, and these are all half inch strand that we are putting, and similarly we are putting 12 mm some nominal longitudinal bar like this, okay, to hold everything together, okay. Now, I need some longitudinal bar to even to keep the stirrups in place. That is the reason I am providing some nominal longitudinal bars, okay. And these are typically not, it will also give you some flexural strength, but these are mainly kept as a hanger bar, because if you see this flange section itself is a 1 meter deep beam. So, we need to put some nominal longitudinal bar to hold the stirrups in place, right. So, this is the thing. So, only thing is here it will be 550, like we have discussed, we have to take the minimum. So, this is how we are going to have the sectional detail, okay. So, let us summarize what we have discussed in this part of the module. We have discussed the fundamentals of shear and compare them with the moment design. Again, shear is a brittle mode of failure. Again, usually we design for flexure and then check for shear, right. But nevertheless, you need to be very careful with your shear design, otherwise the failure can be quite brittle. So, we need to be very careful. And we discussed the failure modes associated with crack patterns, particularly relevant to shear, and then we examine the effect of pre-stressing on behavior, particularly focusing on shear and cracking and shear demand, and then we analyze the web shear and flexure shear cracking mechanisms, and we derive the equations also, how the code is calculating VCR and VC0, and we highlighted the key provisions from IS 1343. Finally, we also solved one example problem, right. So, we illustrated the shear design of a pre-stressed concrete beam through an example. So, with that we will complete this shear part of the module. In the next part, we will be talking about torsion. Thank you.